So the stuff we're talking about now, but like even more extreme. That's what makes a long GRB, long gamma ray burst. And then short gamma ray burst is from mergers of, so like it's basically from an explosion, but it depends like what causes the explosion, right? So the explosion in the case of a long gamma ray burst is either a hypernova, or in the case of a short gamma ray burst is basically a neutron star merger or a neutron star black hole merger. So like two neutron stars in a binary doing a dance together, revolving around each other, losing energy, will finally collide. And when it collides, there's massive amounts of energy released, an explosion, lots of drama. That's basically going to give you a short gamma ray burst. Or a neutron star black hole binary. Oftentimes these things are in binaries. They're like a couple exploding together eventually. What a couple. So Betelgeuse, speaking of supernova, so Betelgeuse is a giant. It has a mass of greater than 7 solar masses, and it's at a distance of only 130 parsecs. When it becomes a supernova, any millennium now, pretty much Betelgeuse, when I was in undergrad, Betelgeuse was already due. Its flux as seen from Earth will be comparable to that of the full moon. When Betelgeuse supernovas and the light from it reaches us, we should be seeing a flux as big as the flux of comparable to the moon, to the full moon, because it's close. There haven't been any Betelgeuse scaled supernovae during recorded history. So during the history of us recording things, there hasn't been a Betelgeuse scaled supernova, but there have been some comparable in flux to Venus. On AD 1054, so in the year 1054, July 5th, in the Julian calendar, a supernova appeared in the constellation of Taurus. Chinese astronomical records report that the guest star had a flux corresponding to m equal to -4, around -4 in the system of Hipparchus. The supernova was also commemorated in an Anasazi wall painting. Today, nearly 1,000 years later, so this was in the thousands, this was in 1054, it is 2025 now, as far as I know. Nearly 1,000 years later, when we turn, nearly 1,000 years later, when we turn our telescopes to the position recorded by the Chinese astronomers, we see the Crab Nebula. If you've heard of the Crab Nebula, a supernova remnant. So that thing, that supernova in 1054, July 5, according to the Julius Caesar calendar, if we point our telescopes to that position where the supernova happened back then, we see the Crab Nebula, which is a supernova remnant. The Crab Nebula is 1.5 parsecs in radius, and its expansion speed, measured from Doppler shifts, is 1,500 kilometers per second. Wow. A little calculation soon shows that 1.5 parsecs is around 1,500 kilometers per second times 1,000 years. The Crab Nebula shows all the signs of being the expanding cloud of debris. It's an expanding cloud of debris from an explosion about 1,000 years earlier. So if you have an explosion, the nice thing is that the debris will slowly, disperse. And guess what? That's how we are here. If the debris from stars exploding did not go everywhere, slowly but surely, there would not be elements making us today.